All right, everybody, good morning. We're going to venture into the most important reaction in organic chemistry, the Aldol reaction. And it's in chapter 19, as you can see. And I'm kind of going out of order in the book because in section 19.2c, there's something called a directed aldol condensation. And it actually breaks down the mechanism into smaller pieces for you. And then when we do the normal aldol, we'll see all the pieces that we did over here, we're going to do again over here. So right here, I have a base called lithium diisopropyl amide. Careful how you say amide, because you don't want to imply that it's an amide, which it's not. It's the conjugate base of an amine, which we call an amide. They are spelled the same, amide and amide. English is a funny language that way. Okay, so what we have is lithium as a spectator, lone pair, minus charge, and I have alpha H's in this molecule. I have 5 of them. 3 of them are here. 2 of them are here. Lithium diisopropyl amide, LDA, is a bulky, strong base, which means it likes grabbing alpha H's on the least hindered carbon. That's all LDA likes to do. So decide for yourself which alpha H is easier to get to. Well, it's the one that's on the end of the chain. Those alpha H's there do not have this ethyl group also attached like they do over here. So these are hindered. They won't even let me draw over there, so I'm taking that as a hint to not draw over there. These are hindered alpha H's. LDA doesn't like those. It bumps into the ethyl group and says, I can't get to them, but I can easily get to this one. Get used to that. LDA will be coming up again a couple more times today. Step 1. Straight up acid-base chemistry, end of story. So let's finish step 1 by drawing the enolate. And yes, the title of the chapter is Enolate. Why is this called an enolate? I don't see an ene. I don't see an O minus. That's what ates have, A-T-E. Well, think to yourself, can this thing become something with an O minus? Yes. Can this thing become an alkene? Yes. How? Resonance. So you don't have to do the resonance, but since we're just starting this chapter, in a little side box here, the much more substantial contributor, the one that spends more time in a resonance form, is this one, because O minus is more stable than C minus. And it's very clear why this is called an enolate. Enolate. And we have enolates, and they are reactive nucleophiles that will attack many things. This nucleophile will attack this carbonyl that we add in step 2. Step 1's over, by the way. And much like we saw all the way through chapter 18, they're attracted to the positive carbonyl. Oh, I don't want to run over HCl yet. I might want to come at HCl without redrawing it. And this is the end of step 2. Wow, I told you this one really breaks it down for you. So in summary, step 1 got you here. Step 2 is where the synthesis happens, is where things are exciting. Here's your new sigma bond. It attacked this blue thing, which is now an O minus. And it looks like the conjugate base of the thing drawn right above it. Step 3. And I changed my mind. I'm going to actually redraw HCl. Step 3, acid base. And we are now at the stage of aldol reaction product. And I already outlined on a Saturday video why I like the name aldol. You might want to look at that. It's not, this example doesn't have an aldehyde in it, but the one talked about last Saturday does. So it has an aldehyde and an alcohol in the product. That's typical of aldols. Also ketones and alcohols. Where's the alcohol? It must be beta. Why must it be beta? Because the alpha carbon was the one that attacked. The beta carbon here is the one that got attacked. So you always get a beta hydroxyaldehyde or ketone for an aldol reaction. It could be, as we will learn later, a beta hydroxy ester as well. Because the aldol really doesn't have to do with what your enolate is. It has to do with what your enolate attacks. And your enolate attacks an aldehyde here. If your enolate attacks an aldehyde or a ketone, we're talking about an aldol reaction. Do you think that's important? Of course you do. He just told us at the start of the video, the aldol reaction is the most important reaction in all of organic chemistry. So, yeah, you better know. As soon as you hear aldol, I got a beta hydroxy to another carbonyl. It's hydroxy beta to a ketone or an aldehyde. And he also said it could have been an ester. And there's your aldol reaction product. This is the aldol condensation product. So from this point forth in all of today's video, I'm going to go with ARP for aldol reaction product and ACP for aldol condensation product. ACP. And what happens during the condensation step is a simple dehydration. This is not a new reaction. This is an acid catalyzed dehydration. How do I know? HCl is an acid. First step in any acid catalyzed dehydration is to protonate the OH to make it a better leaving group. And you're going to generate some Cl- in so doing. Hello. You're going to generate some Cl-. I'll put that up here. And you're also going to generate, maybe I shouldn't have put it up there. Where am I going to go with this? I'm going to go with a baby blue arrow. This guy's going to wander over here for a reaction. And you protonated it. I don't think we have to draw the reaction product from the protonation. As long as we go red first. You got a leaving group after red. You're going to do your elimination with the blue. I hope you see that an alpha H must be removed yet again. There's two alpha H's here. There's only one on the same carbon at the end. It must be removed, one of the alpha H's. and you don't have a strong base to do it, but I have a beta carbon with an excellent leaving group on it, so I won't need much of a base to get the game going here. I got to put an H in here. There's the alpha H. Here's our blue arrow. Comes right down, grabs the H, sigma becomes pi, leaving group leaves, it's water. End of story. What do you get in an aldol condensation? You get an alkene that is between the alpha and beta positions to a carbonyl. Could be an aldehyde ketone later on, could be an ester. Aldol condensation product, alpha beta unsaturated carbonyl compound. And that finishes off the left side here. On the right side, it's a simple aldol. What are the giveaways for a simple aldol? Well, you'll see a product with twice as many carbons as the only reactant. That's a huge giveaway. How many times have you ever seen that? 0. This product has 8 carbons. This reactant had 4. You also need to have a carbonyl and a base. And the carbonyl is typically an aldehyde or a ketone. And the base is going to do what the base has been doing all day. Will do all day. Sorry, the day has just begun. Hydroxide grabs alpha H to make, what's the title of the chapter again? Enolate. We have an enolate. And we made water. Let's talk briefly about this reaction, which goes from pKa 20, pKa equals 20, to something pKa equals 16. I just decided this arrow is highly inappropriate. This is a much more descriptive arrow. We can move our enolate in if we're lucky, and we're not, because the arrow is done too close in time. All right. The ratio of the concentration of the enolate to the unreacted acid here is 10,000 of these unreacted carbonyls, 10,000 of those for every 1 of these. 1. How do I know that? The numbers are on the screen that says that. pKeq here is -4. KEQ is 10 to the positive 4. Means there's 10 to the positive 4 more reactants. Sorry, did I say positive 4? Did I misspeak badly? I think I did. I made 1 product for every 10,000 reactants. I'm starting over. The ratio of 1 over 10,000 is 10 to the -4. That's KEQ. And that's the end of that story. This thing is surrounded by unreacted aldehyde. If you're in a room of 10,001 people, and there's 1 you, and 10,000 people that aren't you, and somebody looks in there, they don't see, hey, there's DTW. They don't see that. They don't even see me. So there's a bunch of people in there. Yeah. But the cool thing is, this thing is surrounded by these unreacted aldehyde. Means they're going to react with each other. And this is exciting because at synthesis, new bond. O minus. Do I have to draw the O minus? Is there a way I can go to OH? I think there's a way I can go to OH because I know I need the OH. It's drawn right up there. It's like, come on, let's do this. Let's not do that. What are you doing? Let's get rid of this. I want this to go here. It's not a quantum leap at all. We can get the intermediate to react with the conjugate acid of hydroxide, which is already on the screen. And yes, the aldol reaction is catalyzed. Cat returns. Oh, I just say meow instead of cat returns, right? There it is. Hydroxide. Back. Did you get a beta hydroxyaldehyde here? Yes, you did. This is a true aldol product, isn't it? It's got an aldehyde and an alcohol. Ald for aldehyde, all for alcohol. Love it. How did you get from ARP to ACP last time? You had to protonate this to make it a better leaving group because this was the acid version over here. You do not need an excellent leaving group when you have a stronger base. In fact, you can't protonate that alcohol with this mechanism at all. There's no acid around. Base takes alpha H, sigma becomes pi, and you're allowed to have hydroxide leave in a reaction that started with hydroxide. Should have students go through all the videos I've made and count how many times I've said that. That'd be good. It's about the third time, I'm pretty sure, just this semester. And there's your ACP. And there's your big picture, complete with Enolate. Oh, sorry about that. I can save over here. And there you have it. End of, well, trying. End of story.